Hello and welcome to the fifth video of the M2 chapter, Centers of Mass. On the screen is an M2 exam question to review all of the work we've done so far in this chapter. Pause the video now if you want to give this a go before I start the solution. So this starting paragraph here, other than the fact that it's all uniform, is basically telling you the same thing the diagram's telling you. And we need to show that to three significant figures, the distance of the center of mass of the lamina ABCD from AD is this. So AD is this edge here, and that's where I'm going to have my y-axis. Skimming down the question slightly, we're going to have to find it from BD in part B, and there's a lot of blank area down here, so I'm going to have my x-axis here instead of the usual place down here. What I need to be careful of then is any distance underneath this down here will be considered negative. So let me quickly put that on. I'm taking this as my y-axis, this one as my x-axis, and I know halfway on the semicircle is a 6, so I'll put that on, like that. Now we need to show the distance of the center of mass from AD. So we need the center of mass of the two separate pieces. The x-axis is splitting it nicely into the semicircle and the triangle. Now we know that the center of mass of a triangle lies along each of its medians, more specifically where those medians intersect. So if I roughly sketch on two of them, the center of mass for the triangle is about here. And I also know it's 1/3 of the way down this line from this edge, and 1/3 of the way from here to here. Alternatively, I can use the coordinates of each of the points of the vertices 0, 0, 12, 0, and 0, -18. And I think I will do it that way this time. This is 12, 0. This is 0, -18. Remember it's minus just because I put the x-axis here, so everything below this point is considered negative. And D is 0, 0. So finding the average of the x-coordinates, 0 plus 0 plus 12 is 12. Divide that by 3, I get 4. So here is 4. For the y-coordinate, which actually we don't need for part A, but we will need in part B, so I'll do that now as well. We've got 0 plus 0 plus -18. Divide that by 3 is -6. So this point here is -6. Again, minus just because it's below the x-axis. Not trying to indicate in any way that we can actually have a negative distance. It's just telling us the direction from this line is down instead of up. And we know on the semicircle that the center of mass must lie along this line because it's a line of symmetry. I'm not going to find the y-coordinate of that just yet because we don't need that, and that's a little bit more complicated than the triangle. All we need is the x-coordinate 4 for this center of mass and the x-coordinate 6 for this center of mass wherever it is along here. I could put it on roughly, it's about here. For part A, that's enough information to get us the answer that we need. So let's go ahead and do that. I'll put the y-coordinates in my table, but I won't actually use that just yet. So we've got the triangle, semicircle, and then the full lamina, triangle, semicircle together. We need the relative mass, which we'll calculate by finding the area of each one, the x-coordinate, and the y-coordinate. I'll fill in the y as much as I can at the moment, and we'll come back to that later. The area of the triangle, 12 times 18 divided by 2 is 108. The area of the semicircle is 6 squared pi divided by 2 is 18 pi. So the area of the full shape is just 108 plus 18 pi. Center of mass for the triangle is at 4 minus 6, and for the semicircle is at 6 something, and for the full shape, x bar, y bar, the things we're trying to find. For part A, we just need x bar, so it's this times this plus this times this equals this times this. 108 times 4 plus 18 pi times 6 must equal 108 plus 18 pi times x bar. Do that calculation and we get 4.68 0.87 ... Here I would be very careful to put this number down before rounding it, because the answer is given to you in the question. You want to just reassure the examiner that you did do the calculation yourself and get this number, and then round it to this number given in the question. Also, because they didn't actually give us a coordinate system, I'm going to switch back into the way they phrased it. We're going to say distance from AD is 4.69 centimeters to 3 significant figures. Okay, that's part A done. Part B, given that the center of mass of a uniform semicircular lamina radius r is a distance this from the center of the bounding diameter, find in centimeters to 3 significant figures the distance of the center of mass of the lamina from BD. So we are going from the x-axis here. If the answer is positive, it means it's above this. If the answer is negative, it just means it's below this. Not that that really matters, because they're asking us for a distance, so our final answer should be positive either way when we turn it back from a coordinate to a distance. This question is from quite an old paper, so they've told you this in the question, but you could also find that out by using the formula given in the formula booklet. As a semicircle, the angle in the middle is obviously pi, so alpha, half the angle in the middle, is pi by 2. Sine of pi by 2 is a 1, so you get 2r, and then pi by 2 here, the 2 comes up on top, and you get 4r over 3 pi, which is what they've given here. So if you needed to work that out for yourself, you could from the formula in the booklet. Using that, we're going to find this missing number here, the y-coordinate of the center of mass of this semicircle. So we've got 4 times r, which is 6, divided by 3 pi, gives us 8 over pi for this distance here. Now we do the same thing as we did in part A. This times this plus this times this equals this times this. So we've got 108 times minus 6 plus 18 pi, 8 over pi, is equal to 108 plus 18 pi times y bar. And that calculation gives us a final answer of minus 3.062 ... So the distance from BD is 3.06 centimeters to 3 significant figures. So although the coordinate was negative, that was indicating that the center of mass is slightly below this line, I had to change that to a positive because a distance is just a scalar and we can't have negative. So the distance is 3.06 to 3 significant figures, about here. So that nicely reviews all of the work so far. In this video, we're going to do something slightly different and consider frameworks. A lot of the process is going to be the same, but we need to know what a framework is before we go much further. So a framework is a shape made up of thin, rigid pieces like rods or wire, and each piece is modeled as having no thickness and no width, just length. But we've got to be careful, because on paper or on screen, sometimes it can be difficult to tell the difference between a framework and a lamina. But the two will give very different answers, so you need to be clear which one you're working on. I will do this. I'll fill the color for a lamina and leave just the border for a framework. So a framework is this plus this plus this, and in the middle this is a hole. So this is like a coat hanger. Whereas a lamina is like a piece of paper, it's got all of this area in the middle included. And what we do to find the center of mass of something like this is to split it at the corners into 3 straight rods and use each of those as if they were a particle on a plane. So like laminas, to find the center of mass of a framework, we're going to split it into separate pieces and treat the pieces like particles on a plane. So in that sense, it's similar to laminas. But unlike laminas, for a framework, we're not using area because they're considered to have no width, so they don't have area, which again is a model. That's not a realistic thing to do in the real world. But as a model, they only have length. So length is going to be representative of mass if it's uniform. That means the longer the rod, the more mass it has. Everything else is very similar. So for frameworks, we need to know two standard shapes of rod. A uniform straight rod that has a center of mass at its midpoint. So if you've got a straight line here, the length is the relative mass, and the midpoint is where that mass is assumed to be acting, the center of mass. We also need to know a uniform circular arc, and that has a center of mass similar to a sector of a circle, r sine alpha over alpha, and this is given in the formula booklet, as with the sector. And as with the sector, it's assuming that you've got a center point here of the full circle, as it would be, coming out, of course, with a line of symmetry down the middle, and like the sector, this angle in the middle is 2 alpha, and the alpha that's in the formula is half of that. So we've just got alpha here, with the radius of the circle here, circle center point here, and then in the formula booklet, we've got the formula, here it is. So circular arc, radius r, angle at the center 2 alpha, here is the formula from the center. So it's measuring from the center this way. Very similar to the sector of the circle, but don't get them mixed up because they are not the same. As you can see, this has a 2/3 factor in it. So with this information on the screen here, and the knowledge that we're using length as the relative mass instead of area, the rest of the process stays the same. So here we have the diagram shows a framework made up of uniform rods, and you can see that this very easily could be a laminar, but because it uses the word framework, these are all little rods connected together, and in the middle, a hole. There's nothing here. We're just looking at the rods. Find the distance of the center of mass of the framework from AF here and AB here. So they're giving us our obvious XY coordinates. I'll put them on. Here is obviously going to be the x-axis. Here the y-axis. And we're going to use the midpoints of each one of these. Going round very quickly, here we can see this is going to be at 0, 2. This, if you calculate from the 8 and the 6, FE has a length of 2, so the midpoint is going to be at a 1, 4. Here, the midpoint is going to be at 2, 3. Here, the midpoint here is 3 centimeters in, but we also have the 2 centimeters away from the y-axis, so this is at 5, 2. Over here, this is obviously 8, and the y-coordinate 1. Finally, the long stretch on the bottom is 8 centimeters long, so the midpoint is here at 4, 0. So I hope you can see there's a lot more involved in terms of the midpoints. We're going to have quite a few different particles we're adding together, but there's less effort involved in finding the relative mass because we just take the length of each one. So if I were to set out a table like we had before to really show it's very similar, because they're all straight lines, I'll use their endpoints to name them. We've got AB, BC, CD, DE, EF, and AF. And then at the end, we've got the full framework. Relative mass, which we're going to use the length to calculate. X-coordinate and Y-coordinate of the center of mass of each piece, where X bar, Y bar is the center of mass of the whole framework. So A to B is 8 centimeters long, and its midpoint is 4, 0. BC is 2 centimeters long, its midpoint is 8, 1. CD is 6 centimeters long, its midpoint is 5, 2. DE is only 2 centimeters long, and its midpoint is at 2, 3. EF is 2 centimeters long with a midpoint at 1, 4, and AF is 4 centimeters long with a midpoint at 0, 2. That gives us a total length of 24. I was quite keen to lay this all out in the table in the same way that we've done with laminars to show that the process is very similar. But you might notice in the textbook they don't do this, and the more you do these questions, the more you might be able to jump over this table and just go straight into a vector equation using the lengths times the midpoint position vectors. Because what I'm doing here is basically just rewriting all that information in equation form, because there's no area calculation to do. So if I put all of that here, then we have to do the addition of all of these, and that is equal to 24 times x bar y bar. And that gives us a total on the left hand side of 8436. And then we just divide both of those by 24, which gives 7 over 2 and 3 over 2. So the distance from AF is the x-coordinate, 3.5 centimeters, and the distance from AB, which is my y-coordinate, is 1.5 centimeters. And there we have our final answers. Our second example is very similar in the process, but involves a semicircular arc. So find the position of the center of mass of the framework constructed from a uniform piece of wire bent into the shape shown over here. The wire BCD is a semicircle, center O, of radius 3, and the wire BAED forms 3 sides of a rectangle. The XY coordinate I'm going to choose here is going to go through O like this. And it's worth noting that about the x-axis, this shape is symmetrical. So the wire bent into a semicircle shape has center of mass somewhere along here, and so does the 3 sides of the rectangle here, somewhere along here. So I don't actually need to do a calculation to say that the center of mass must lie along this axis here. That gives me a y-coordinate of 0. The only question is how far along here, the x-coordinate. To do that, I do the same as before. The center of this point here is on the axis, so that's -2, 0, because from here to here is the same as this, 2 centimeters, but it's going in the negative direction if I've taken my center point here. So we've got -2 and 0 on the y. For this rod down here, ED, center of mass is in the midpoint, so that's a -1, and down here, -3. Midpoint of this one up here is -1 on the x again, and 3 on the y-axis. For the semicircular arc, it's about here, and that is r sine alpha over alpha from O. So if I call that G, then OG is equal to this distance. And for a semicircle, the angle here, pi, alpha is pi by 2, and sine of pi by 2 is a 1. So if I put pi by 2 in here, the 2 comes up and we get 2r over pi. So for a semicircle, this is 2r over pi. For this semicircle, radius of 3, that's 6 over pi. So this is 6 over pi on the x-axis, and of course 0 on the y-axis. Now I'm ready to make my table. We've got AB, AE, ED, and the arc from B all the way around through C to D. Then I've got my full framework shape. Relative mass is the length of each one. For AB, that's 2. For ED, that's also 2. For AE, that's 6. And for BCD, the arc is 3 pi, half of the full circumference of the circle. The full length then is 10 plus 3 pi. Then the x and y coordinates for the centers of mass. And even though I know the y coordinate is 0, I'll go through the calculation just to show you that it works out. For AB, that's -1 and 3. ED is -1 and -3. There's a symmetry there. For AE it's minus 2 and 0, and for the arc is 6 over pi 0. And you can see that with a 0, 0, plus 6, minus 6, the left hand side of the y is going to be 0, divided by this will give you a y coordinate for the centre of mass of 0. And x bar, which is the one that we don't know yet. Following the usual calculation, this times this, plus this times this, plus this times this, plus this times this equals this times this, we get minus 2, minus 12, minus another 2, plus 18 pi over pi is just 18, equals 10 plus 3 pi times x bar. So x bar is equal to 0.10296 dot dot dot, and we're going to write it to 3 significant figures, which gives us 0.103 centimeters. So there are a few different ways that we could wrap this up. What I'm going to do is I'm going to take this x coordinate and add 2 centimeters to it, so that I can say from AE, the centre of mass is 2.103 centimeters along the line of symmetry. And that's how I'm going to phrase my final answer, is 2.103 centimeters from AE along the line of symmetry. The question did give us O, so if you wanted to, you could have left it at 0.13 centimeters from O along the line of symmetry, but in that case I think you would have to specify towards the arc or away from AE. There would be a little bit more there to say. But so long as you're clear, it shouldn't matter which way you write it. I hope that's enough for you now to have a go at some of the questions in exercise 3E, and this sort of wraps up a lot of the centre of mass work. From here on in, we're going to be looking at using laminas and frameworks to find various angles in different situations, and a little bit at non-uniform systems. Maybe I'll see you for video 6.